she'll go to YouTube, she'll watch a video, and it'll be good. Okay, and um, so why are we recording this one? Well, maybe some of you guys won't get it and you'll want to go back. And two, I just need to make sure it records appropriately. Real numbers. Here we go. Natural numbers. I teach Emily to count. What does she start with? 1. Those are the natural numbers. First time I heard Kiera count to 10. She counted to 10. I'm like, great. And she says, do you want me to do it again, Dad? I said, yeah. She goes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm like, what? Like, I never, where'd you learn that? I watched Dora. So, wow. Cool. All right. So, yeah. She's smart. So we've got a natural numbers, and the symbol that we use is an N, but we put 2 lines with that first leg there, so to speak. That's symbol for natural numbers. All throughout time, people have been able to generate these numbers. There came a time where they added in another number for whole numbers. What is it? 0. And it may seem simple to say 0, but it took many cultures, many different years to come up with that concept of 0. But obviously, it's very important in our mathematical language. Integers add negative numbers. So -2, -1, 0, 1, 2. Integers is a very important study in mathematics, especially if you take a course called, say, number theory. Because we do talk, there are certain things in life that are integer expressions, such as people. We don't talk about tenths of people or hundredths of people. So got to sometimes come up with integer expressions, and so that's an important study. Rational numbers. What's the word of rational? Starts with an R. Ratio. So ratio is another way of saying, starts with an F. Fraction. So can you give me an example of a rational number? 2/3 is a rational number, which is great because so is 0.3 repeating, because it can be expressed as 1/3. But so is -10/5. It simplifies to -2. So true or false? All integers are rational numbers. It is true. All integers are rational numbers. True or false? All rational numbers are integers. False. Give me an example of a rational number that's not an integer. 1/3, 2/3. Okay, those are all examples. Like 0.1, that's a rational number because it can be expressed as 1/10, so on and so forth. We use a Q symbol for that. Now, there are some numbers that are real. We use this big R for real numbers. There are some numbers that are real, they're not rational. They are referred to as irrational. What numbers are irrational? Pi. So we got another one. How about E? Did you learn about natural logarithms last year? Okay. And so E is the base for the natural logarithmic function. It's like 2.718, so on and so forth. The square root of 2, that's an irrational number. If you were to take the sine of, say, 36 degrees, that's an irrational number. If you were to take the log of 14, that's an irrational number. Whereas the log of 10 is a rational number. In fact, it's natural because it's 1. Okay? So, irrational numbers are special. There was a time in our world where they didn't think that irrational numbers existed. They're like, that's impossible that numbers could exist and not ever repeat themselves. And it was kind of tied to some of their beliefs. And if you talked about irrational numbers, it would actually burn you at the stake. I'm not kidding. Yeah, it was very connected with their beliefs. So you didn't want to, you're kind of viewed as an outsider if you ever thought that the square root of 2 is actually a real number. So anyway, to suggest that there are real numbers suggests that there are also what kind of numbers? Imaginary, otherwise known as complex. So outside of here sits, say, I, or say 3 plus I. That would be a complex number because it has a real part and imaginary part. Those are complex. People, when they first came across imaginary numbers, they said, well, what good will ever come of imaginary numbers? Like, it's kind of pointless, right? I mean, what will ever come from that will benefit society. Well, 100 years later, a man by the name of Leonard Euler developed more the study of complex numbers, and they ended up using that to develop what we call alternating current electricity. We have two types of currents for electricity, alternating and direct. Your phones, which one do they use? Direct, because they run off of a battery. This smartboard runs off of alternating current. If you had direct current for everything that you use, we would have to have a power station on every block of the city in order to power our services. That wouldn't be good, would it? So alternating current's great, and that only comes through imaginary numbers. Aren't you glad? Yeah. So this is good stuff. Do you ever think about what the square root of I was, though? You don't know. No, not even worth guessing really at this point. In fact, later on, I will teach you second semester how to find the fifth root of 3 plus I roots of 2. It's kind of ridiculous and it makes your head hurt. There's actually 5 solutions to it, but I'll teach you how to do that. There is an answer. There is an answer. You don't even have to like it, but you should be able to say, wow, I can't believe that we can actually do something like that. Doesn't mean you're necessarily be very good at it, but we'll teach you. So, all right, let's go to something you know how to do. Let's take these real numbers and let's put them as sets. So we have the set of 3, 5. Okay, we have brackets on both. It says express as a graph and an inequality. I like to do the visual first, which is the graph. So as I graph it, I plot 3 and I plot 5. Open or close circles? Why close circles? Because you see the brackets, so we join them together. And then for the inequality, I like to think of it as x represents all the numbers that are part of that solution set. So x sits between the 3 and the 5. How does x compare to 3? It is greater than or equal to 3. How does x compare to 5? Less than or equal to 5. And so those are my two expressions. One is a graph and one is an inequality for that interval. Go ahead and do B, C, and D on your own. When you get an answer, be confident and proud and put it on the board. Okay, nice work. It looks like we've got good stuff here. We are going to take the second one. We're going to quick write the inequality for it. We have negative 2 and 0, and we're going to put x in between those. Okay. And then the next one, x is less than 5. And then this last one, it is written backwards, but technically that is still correct. You can write it either way. So if you're going to write it the other way, then just again make sure that the large part attaches onto the x. And there you have it. Good. So yeah, flip it over. Any questions on that front page? Going once, twice, 3 times. Here, write an interval for the following and graph the set. So negative 3 to 9. Again, I always like to start with the graph. Open circle, close circle. And so as you express that as interval notation, again, we have negative 3 and we have 9. And we have a parenthesis and a bracket. Anytime you see the equal sign or the circle, that means bracket. Please do letter C on your own. Don't worry about B and D. That would be just redundant. Don't worry about B. Why can't we put a bracket on negative infinity? You can't stop it? Yeah, there's absolutely no spot on the number line where you could point to it and say, that's negative infinity. I mean, that's just silly, right? It's like, well, just go over here and then a little bit further, right? I mean, the idea of infinity is quite ridiculous, isn't it? You know what I mean? So it's pretty big. Okay. I wrote a song about it. We'll see. I usually save it for calculus, so well. All right. Now we're going to switch it up a little bit. We're going to teach you something a little bit new. If you see this symbol, that is called a union. And that means the combined group of the two elements given. Whereas if you see this symbol, this means intersection or the overlap of the sets that are given. So it tells us find the indicated set if A is from -2 to 6, B is from 0 to infinity, C is from -6 to 1, and provide a graph. So A union B, we're wondering what that means. I'm going to write it out as a graph first, and then we'll express it in interval notation. So there's my graph. A, -2 to 6, B, 0 to infinity. I'm simply going to write -2, 0, 6. And if you do want to put infinity, just put it on the end there so that we understand you're going to the direction of infinity. So just don't put a mark on there like it's actually infinity. So just it's in that direction, okay? So A is going to go from -2 to +6. B, 0 to infinity. So when it asks for A union B, it means that you can either be part of A or part of B or part of both of them. So I'll give you a number. You tell me if it's part of A, B, both, or none. Okay? 20. It's only part of B, right? How about 3? Okay, how about -1? It's just part of A. And how about -10? None. So this is the only spot where it's not part of either one, correct? So the solution to A union B is from -2 to infinity. It doesn't have to be part of both. It just has to be part of one or the other or both. You try A union C. So the overlap, I'm sorry, the combined grouping should be from -6 to +6. Any questions on that? Okay, then the next one says A intersect B. So that means what is the overlap? It means it must be contained in both sets. So you tell me, I already have the graph. It's over here in A. What is the number that's contained in both sets? No, you're good. Thank you. What's the number contained in both sets? Sure. 6 would be contained in both sets. 2 would be contained in both sets. In fact, everything in this region right here is contained in both sets. Agreed? So A intersection B will be from 0 to 6. You try E. B intersect C. Yes. Oh, I made a mistake. You're absolutely correct. You have a bracket there. Should come up with 0 to 1. Yes? If we added in C as well from -6 to +1, I'm sorry, if we added in A from -2 to +6, would that change our answer? Again, we're looking at the overlap between all three. It would still just be within this region here, correct? It would be from 0 to 1. So just a little bit new to see that you have, that intersection and the union piece. So my question to you is, if on the test you get an inequality, can you express it as a graph and as an interval? Great, then you can ace the first part of the test. Good job. Let's look at the second part of the test. Yes. Yep. So for letter F, if I were to do the same kind of thing here, and I were to then include A, and it says A is from -2 to 6, so open circle and close circle here. I'm looking at the intersection between all three. And as you can see, the intersection between all three is still right in, this region right here, isn't it? So it's still from 0 to 1. So it does not change. Good question. Any others? Okay. Probably the most points taken off on your test generally comes from the exponent section. So we'll do a little bit today, and you'll do the rest on Monday. You'll have a decent amount of work time on Monday as well to work over it. So let's begin with some basic rules, and we'll try some sample problems, see if we can catch some mistakes that you might make along the way. And anything to the 0 power is y. Anything divided by itself is 1. And using the property of exponents, x to the fifth over x to the fifth is the same as x to the 0. So therefore, x to the 0 is 1. That's why. Convinced now? Because otherwise it just looks like somebody made it up, right? And mathematics is never made up. There's always a reason. Okay, on 2, we have a to the m times a to the n. They have the same basis, so what do you do to the exponents? You add them, so a to the m plus n. And what if you're dividing? What do you do to the exponents? You subtract, so a to the m minus n. What if there are two terms, both a and b, being taken to an exponent? You take a to that exponent, and you take b to that exponent. And if you're dividing, you'll do the same thing. A to the n over b to the n. What if the exponent is negative? Flip what? Flip what's on the inside. So b over a raised to the nth term. So b to the n over a to the n. We don't like negatives, do we? In golf, you might like negatives, like, you shot a -1 or something. It'd be pretty impressive. Like, if you were to golf and you were able to hit the ball into the hole on one shot, and then it were to bounce and go into the next hole, I guess that would probably be a 0 then for that one. But then if it goes into the next, I think you should get a negative at some point. Probably never happen, huh? Any golfers here? Ever get a hole in one? No? I played putt-putt golf this summer. I got a hole in one a couple times. So, yeah, yeah. All right, next one. If you have negatives, again, you move them to where they're not. So b to the m over a to the n. We have some nice properties that involve radicals. If you have the square root of a times b, you can rewrite that as the square root of a times the square root of b. So you can take factors and pull them apart and just include radicals above them. If you have radical over radical and it's the same type of root, so square root, you can rewrite it as 1 square root. And then another thing that is helpful sometimes is rewriting radicals so that they have rational exponents. So this is equal to a to the something over something. Does anybody remember what goes on top and what goes on bottom? M is on the top, n is on the bottom. So n is referred to as the index. Technically, that's what we call it. It's the index of the root. Everybody got that? Let's try some sample problems. 4 to the third, 64. Negative 2 to the fifth. So we take 2 to the fifth, and then we make it negative. No. No. There's no negative value to the exponent, so there's no flipping that's involved, okay? If it was negative 2 to the negative fifth, well, then you would have negative 1/32, okay? That's a different scenario. But suppose I wrote this, negative 2 to the fourth. It is negative because the order of operations says that we take 2 to the fourth to get 16, and then we apply the negative to get negative 16. If you saw negative 2, that quantity to the fourth, then a negative times a negative times a negative times a negative will give you a positive. See the difference between the two? Make sure you don't make that mistake, okay? That class. So. All right, here we go. Negative 3 to the third. Anybody? 11 to the 0. You guys are getting good. Square root of 144. Do we list negative 12 as well? If the problem said x squared equals 144 and find the solutions, we know that there are two, and we list positive 12 and negative 12. But if you're simply asked to evaluate the square root of a number, you list what we call the principal root, the positive root, just 12, okay? Cubed root of negative 125. Fourth root of 81. See if you can do h on your own. Should get 8/9. Anybody make a mistake that they're willing to share? Because then we'll all learn, and we like to learn. No? Okay. Okay. 6 to the first. Awesome. Good. Looks good. We appreciate your star quality of courage in saying that you are going to step up and show us what you did. Yep, 100% incorrect. Yep. But But we can all understand that, right? I mean, we get it. You know, you multiply these, you add these, but they got to have the same bases if you're going to add the exponents, right? Okay. So that's why that's why we do it. So we learn from our mistakes along the way. So you weren't the only one erasing your answer. So, okay, the next one, 1 over 3 to the third. 1 over 27 times 6 squared, 36 over 1. 26 over 27, they're both divisible by 9, so 4 over 3. Some people look at square root of 5 times square root of 45, and they say, well, I know what 5 times 45 is. Anybody give that a shot without a calculator right now? 4 times 40. 225, okay? So many of you wouldn't go that far to actually calculate it. 5 times 40 is 200. 5 times 5 is 25, so you get 225. Like, okay, the square root of 225 is 15. But suppose you're not going to do 225. You're not going to multiply it out. Let's do an easier way. Square root of 45, you can break it up into square root of 5 and square root of 9. So now, square root of 5 times square root of 5 is just 5, and square root of 9 is 3, so you got 15. So sometimes it's a quicker way to be able to evaluate expressions as opposed to actually, multiplying out. Sometimes you can use that principle. Try to do the same thing for k. A lot of people wouldn't do 3 times 48. They would, try to find another way. Square root of 3 times square root of 3. 3, square root of 16, 4, so we get 12. And the last result, 2 to the negative third over 4 to the negative 2. So we will flip them. So we get 4 squared over 2 to the third. And that would be 16 over 8, which is also dos. Spanish for 2. I did watch a little bit of Dora. I like the backpack. The backpack is swiper. No swiping. Shows are so much more educational today, though. I mean, it's so much more educational. When I was growing up, there was a rabbit running around and a coyote running around and a bird running around. And they were dropping anvils on each other's heads. I mean, that's like Looney Tunes. You're watching that. So destructive, but great shows. Great shows. So cool. Wish I would have had one of those. By age 6, I think she had read more books than I have in my entire life, which is really bad. I'm a bad example. Bad example. We're going to do 2 more examples. Simplify the following expressions. Eliminate any negative exponents. You guys are just going to deal with the radicals here. Can I take square root of 18 minus square root of 200? What must I do first? Simplify square root of 9, square root of 2, square root of 100, square root of 2. In order to subtract them, the radicand, the number underneath the radical is referred to as the radicand. They must be the same. The square root of 9 is 3, so 3 roots of 2 minus 10 roots of 2. It's negative 7 roots of 2. Now, what's different about problem B? Cubed root. Give me an example of a perfect cube. 8, 125, 64, 27, through 16. Perfect cubes, your brain might not go the right way. You might have to make a little chart. But 8 is a perfect cube. So the cube root of 8 times the cube root of 2. Plus 2 times the cube root of, what divides evenly into 250? 125 is a perfect cube. So it looks like I get the cube root of 2 to pop up. And that'll be my radicand, 2. Cube root of 8 is 2, so 2 cube roots of 2 plus cube root of 125 is 5 times 2 is 10 cube roots of 2. I get 12 cube roots of 2. And that's that. Okay? Nice little introduction into some exponents. We will do more difficult examples on Monday and hopefully clarify any concerns or questions there. I will say that would be to your advantage to really make sure on Monday and Tuesday you check your answers from the exponent section. Again, by far and away, the most mistakes that people make during this first unit is in exponents. Here you go. You have an assignment. 1.1, page 12, 29 through 40. That will take care of your intervals and inequalities and that stuff. And then 1.2, page 23, right there. So you can combine them all on one page if you would like. But please don't just number your paper right away, though. You know, if any of you are horizontal writers, just write 29 and do the problem. Then write 30 and do the problem. You know, go ahead. Anybody, somebody who just writes them all down right away? Nobody? First class ever. So it's nice to space out that work. All right, have a great weekend. You can get started. There's books up there, as you can see, if you want to grab some. Otherwise, if you brought your own, go ahead and look. If you have questions on the entrance worksheet, I can answer those as well.